Bienvenidos al seminario web. Por favor, espere. El seminario comenzará en breve, así que le rogamos que permanezca en línea. El seminario comenzará en breve. Por favor, permanezca en línea. El seminario comenzará en breve. Por favor, permanezca en línea. La emisión está comenzando. Todos los asistentes están en modo de solo escucha.
Hello to everybody and welcome to today's webinar. I'm sorry for the delay. Could you let us know in the question box if you can hear us? Perfect. I see a lot of responses coming in. Thank you very much for letting us know. And I can also see that some more people are joining us. And I'm delighted to say that we have participants from all over the world joining us today. Thank you very much.
Hey, can you hear me?
Yes. Hi, Phil.
Hey, okay, sorry about that.
Could you share your screen?
I'm
with
trying.
the audience?
Yeah. Okay, show my screen. Can you see my screen now?
Yes, we can see your desktop.
Okay, yeah. Excellent.
Perfect.
Okay, all right. Sorry about that. Okay. Did you introduce, or do you want to start?
I can start, yes. So again, welcome. Now we are ready to start with our webinar. My name is Milena, and I will be your host today. I already just established that the question box is working pretty well, and please feel free to type in any questions that come up during the webinar, and we will be answering as many as possible at the end of the webinar. If there are questions that we don't come to in the webinar, we will answer them afterwards in an email.
Excellent.
So before I start, I would like to introduce Rolf, who will be presenting the use of rheology in the formulation of pharmaceuticals. So here you go, Philip.
Hi, thank you very much for introduction, Milena. And today we're going to be looking at the use of rheology in the formulation of pharmaceuticals. And so we're going to touch on several different areas. First of all, small molecule pharmaceuticals, and then biotherapeutics and injectability, viruses and vaccines. There's been a lot of research being done in that. And also medicinal nanoparticles, lithium and other things like this, nutraceutical foods. I'll be speaking briefly about abbreviated new drug applications and the requirements of the FDA in making those. So when you're looking at pharmaceutical rheology, you could be using rheology in the area of formulation, obviously, or in processability, or in the performance of the final product. So the final product obviously wants to be stable, and the formulation plays right into that stability. So there's some aspects where these things tie in together, and also the material needs to be processable. So you need to know how much time maybe to mix the components together to get homogeneous mixture. And so we can see these things with rheology. And so actually with a rheometer, you can simulate nearly all of the processes that a sample will see throughout its lifespan. So if you think of mixing, maybe in manufacturing or pouring, pumping, these things might be able to be mixed, measured with a viscometer because they're in the moderate shear rate range. But with a rheometer, you could actually also look at the storage properties, whether the material is going to sediment. Obviously, that would be a very, very low shear, or whether it's going to level or sag. If you had delayed release vehicles, then that would be a very low shear rate process, dissolution, or maybe injection. Obviously, that's a very high shear rate process. So with a rotational rheometer, we can actually simulate a very, very wide shear rate range, up to 10 to the 5 reciprocal seconds. So we can actually see things like injection as well as sedimentation with the instrument. So here's a quick table of some of the things that we're going to discuss today. So maybe the solubility or the dissolution time of a product into the medium which it's being dissolved in. So that obviously would be relevant for the efficacy or bioavailability of a drug. If it's highly soluble, then it's going to be more bioavailable. If it's less soluble, then maybe less so. Obviously, the injectability, the suspension stability, that would be the sedimentation. I didn't have a picture at hand easily to show something sedimenting, but obviously sedimentation occurs over long periods of time if something's not stable. Topical creams, which obviously are a cream or a lotion or an ointment with the API in it. And so the rheology of that cream is very, very important. You don't want it to phase separate. You want to see how low viscosity it is when you rub it, and whether it's going to soak into your dermis and epidermis. Nasal sprays, we'll touch on these, tablet coating, and ophthalmic treatments, hydrogels and things like that, and also hydrogels in delayed release vehicles. So there's a lot of different uses of rheology in the pharmaceutical industry. And because of the time available, I'm really going to be able to just touch on some of these. But let's look firstly at biotherapeutics. So large molecule biotherapeutics, such as monoclonal antibodies, need to have a low viscosity, less than about 10 centipoise, to be injected at home. And because you need a very high concentration of these in your body, a reasonably high concentration to have any therapeutic effect, we've been seeing researchers adding more and more of the monoclonal antibody biotherapeutic, and the viscosity goes up. And so this is a picture here by Spin Analytical, but it shows here that you may have a lower viscosity mixture, but when you shear it, sometimes the material packs together, and this with dipole-dipole interactions can lead to an increase in viscosity. So we can actually reduce the viscosity by changing the structure of a sample. So here we have the molecule calmodulin, which is a calcium binding protein. And there's the apo structure on the left, which is open, and the hollow structure on the right, which is closed. And actually you can see, although this picture is almost the same size, you can actually see that this has shrunk slightly, and it's much a tidier molecule, as when it's bound to this calcium, you see in yellow here, it's actually shrank slightly. And so the formation of that tight helix in red makes the molecule a little bit smaller, and so it reduces the viscosity of the injectable drug. So here's the hydrodynamic radius. It's gone from 7.4 nanometers down to 4 nanometers. And so it is smaller. Obviously, these parts are tied together. It's not going to swing out into a larger radius, but the viscosity goes down by 8-fold. So even though the radius only dropped maybe half, or not even half, the viscosity has gone down 8-fold with the hollow structure. So in this case, it would be wise to bind it to calcium in the formulation such that it would be a very low viscosity for injectability. And so we found that by maybe by changing the pH also, or by changing the structure of the sample, you can change the viscosity. And the good thing is that on the Connexus Ultra Plus rheometer that we have, you can test very, very small volumes. This is 40 microliters of sample, and here's water, millicu water sample. We found a mean viscosity value at 20 degrees C of 1.008. So it's off maybe in the third decimal place slightly, which should be 1.000. And so we're off by 0.008 of a centipoise, but that is highly accurate with only 40 microliters of sample oil. So rotational rheology is able to test very small samples, even with a cone 1 degree 20 these days. We're going to shear at moderate shear rates, and we'll be able to see the viscosity of the sample and therefore whether it's injectable or not. Now, another application would be things like nasal sprays or inhalers, and we want to see the aspiration and bioavailability of that drug. Now, there's quite a lot of math involved with this, and I don't want to take you through it all, but if you know the flow rate and you know the diameter of the aperture of the sample, and the rheology will relate directly, therefore, to the particle size. So this is a graph here by Lefebvre on industrial finishes, and he's looking at mean droplet diameter. Let me just get the laser pointer here. Mean droplet diameter on the left versus spray pressure. But so obviously, if you spray at higher pressure, the viscosity or the droplet size goes down. As you go to higher viscosity, the droplet size goes up, and you can see that that is also a kind of proportional relationship. So the higher the viscosity, the larger droplet size. The lower the viscosity, the smaller the droplet sizes for spraying. This is a Hagenbach treatment. So if you want to see the distance that a droplet will travel before it drops, then you can use this Hagenbach model to calculate. And so you just need to see the velocity in the flow field there and gravity, and then 2y will show you the amount of drop of the particles. There's a lot of different treatments of this, and I don't have time to go into it at much detail now, but if you want to know more, please do contact us. We did actually have a separate webinar on this, Rheology of spray materials. But this is a nice graph, a nice few photos from Jenny Christianti with Lynn Walker's group at CMU. And she showed for Newtonian liquids, you see these atomize quite cleanly, but for a viscoelastic fluid, it doesn't atomize very well at all. This is an extreme situation where the material is just coming out like a string, really kind of like a cobweb, and it's not atomizing cleanly. So to have a cleanly atomized material, you need to have a lower viscosity, and also lower surface tension will help, or higher surface tension will help take it into atoms rather than to a string, and the density plays into it as well. And also for viscoelastic fluids, we can see the jet length, the jet diameter, and the interfacial breakup. So if you know the shear and extensional rheology, you can calculate these things. Now, another application of nasal sprays isn't obviously that you just spray this into the nasal cavity, but that it stays where it should stay. So this is the inside of somebody's nasal cavity, and if you spray the droplets in here, and this is a low viscosity liquid like water, then what happens is over a period of time, this would actually just run down in your throat and you swallow it, and it's not being very effective. But we found that if you increase the viscosity slightly, I say we, science has found that if you increase the viscosity slightly, you can actually impart some yield stress, a vanishing yield stress here. So it's a very low viscosity material, generally at high shears, but at low shears, it can actually stick on the outside of the material of your nasal cavity. And so you have the good bioavailability, and the best, obviously, if it really stays there where it should be, and it will stay there for a long time. And this can be done just by adding very small amounts of cellulose. So in this case, maybe carboxymethyl cellulose. Now, another thing that rheology is used for regularly is in tablet spraying. Now, that tablet coating ideally needs to be as high as solid. You want it to be able to coat the surface and then dry out. You don't want it to soak into the center of the tablet. You want it just to coat the surface and then dry out quickly in the drying oven. But it needs to be able to flow cleanly. So we need to have a very high you need to have a high solid sample with a low viscosity that can be sprayed. And so this is our rheology context now. Let me go back. Sorry, I skipped that. So at the high shears for spraying, the viscosity needs to be low enough to coat and to flow over those tablet surfaces. But ideally, it needs to be at high solids. And you do this by increasing the particle size distribution. If you have a very wide particle size distribution, you can get to pretty high solids loadings while keeping the viscosity moderately low, and obviously keeping the pH nearer to the isoelectric point without making the sample unstable. And so this reduces the viscosity even at high solids loadings, such that the spray coating will be sprayable and dry out quickly. Now, another application here are lotions and topical creams. So if you think of the life of a topical cream, obviously it has a long period of storage, maybe in a shop or in a warehouse, and you'd hope that it's not flowing at all at this case. But if it is flowing, it should be flowing very slowly. And so we would characterize the viscosity at a very, very low shear rate to see if the viscosity is high enough, or hopefully it has a yield stress. And that will indicate that it has some storage stability. And then there's this time when you come to pump it. So you pump it out onto your hand, and the shear rate from pumping through that dispenser is about 10 reciprocal seconds as it comes up through the nozzle there. And then you see it on your hand and you say, oh, I'm not sure if I like this stuff. It's too low in viscosity, or, oh, this is nice and thick and creamy. I like it. So this is actually only a few seconds of your experience of a sample, but it's a moderate shear rates, let's say around 1 reciprocal seconds. Does it flow off your hand? Does it stay in place? Is it pleasing to the touch? And does it look aesthetically pleasing to you? And then obviously, lastly, you're going to rub that topical cream or lotion into your skin. And so you want to see how it feels. Now, if it has a vanishing viscosity at high shear rates, then it will actually feel much easier to rub in. And so we can characterize all these flow properties with a shear rate sweep on a rheometer. So at high shears, if the viscosity is very low, This would indicate that it rubs in cleanly, or rubs in easily, and also maybe soaking into the dermis or epidermis, so it might be better for a drug delivery vehicle. But if it's thicker, then it's probably going to be more of a barrier cream. And here, obviously, at the low shear, we have the storage stability, and then somewhere in 1 to the 10 region, you know, we have the pumpability and the aesthetic feel of it. So all these things can be characterized with a viscosity flow curve. Now, the FDA came out with some guidelines for topical creams, and that's if you were going to make a generic drug with and just copy one of the original innovators, then you can have an abbreviated new drug application. And the FDA's guidance said that you need to look at the appearance and analysis of the polymorphic forms of the drug in the drug product, and also analysis of the particle size or globule size, and the pH and the crystal habit and the gravity. But then it said that we also need to refer to the rheology, and these are the specific guidances from the FDA. Analysis of rheological behavior, which may be characterized using a rheometer that is appropriate for monitoring the non-Newtonian flow of semi-solid dosage forms. The following evaluations are recommended: the complete viscosity flow curve, so that could be shear stress versus shear rate, or viscosity versus shear rate, with multiple data points across the attainable shear rate range, or until low and high shear rate plateaus are identified. Also, the yield stress value of the material, if it gives you any plastic flow behavior, and the linear viscoelastic response, so you can see the storage and loss moduli versus frequency. And so actually, there's a quick case study here. I have some generics as well as the reference listed drug for an ointment. This is actually an ophthalmic eye ointment, and we did these 4 tests. So you have the yield stress test, curve, and then we had a quick amplitude sweep and then a frequency sweep. So not in the correct order here. So this is the amplitude sweep data. This is one of the preliminary tests. So if you oscillate a sample in very, very small amplitude, the structure is completely maintained. But as you go to larger and larger amplitudes, the structure starts to break down. So we have what's called the linear viscoelastic region, and then we can see we're starting to break the material. If I'd gone to larger strains here, it would have come right down to a lower modulus. We have some rebuild going on there from the loading, so please excuse this going up on the left-hand side. If I'd loaded it and waited, this would start on a flat line here, but we're inside the linear viscoelastic region until we can see it starting to drop point after point after point. And it looks to me like the linear region here is after about 0.1% strain, right? So you see this is a linear region and it's starting to drop at these higher strains. So looking at a smaller strain than outside the linear region, maybe we'll go to 3e-2 or 2e-2% strain. And now we can do a frequency sweep. And this will show us how elastic the material is, that's the red line, and how viscous the material is, that's the viscous modulus in blue, and also the phase angle, that's the tangent of the phase angle is the viscous divided by the elastic modulus. And so we see here all of these samples are about the same in their viscoelastic nature, as in the viscous to elastic structure is about the same ratio, the phase angle is about the same. But you can see here these new generics are actually slightly more viscous or higher modulus than the reference listed drug, which is softer. Here's the yield stress result. So again, you can see that the generic formulation in this case had a higher yield stress. So in this case, what we do is we're applying a stress ramp and seeing the stress increase and increase and increase with time. And then there's a peak of stress, of viscosity rather, at a certain stress, and this is called the yield point. And say here it would probably be around about 80 pascals. And then the reference listed drug has a yield stress of about 45 pascals. So you can see here that the good thing is that the the new drug that we're developing has a good reproducibility. The two different sample loadings have very reproducible results, which indicates good homogeneity. And that means that it's been a good mixing, good manufacturing process, but maybe a little bit overly viscous, too much yield stress here. And then lastly, the viscosity flow curve. And this again shows you a fantastic reproducibility. So you can see for samples 1 and 2, you can see that the samples are very good overlay there, but the reference listed drug has a much lower viscosity. So we'd probably need to soften the material up a little bit, or add some lower viscosity oil or liquid to the material to stop it being quite so viscous. All right, so that was a quick overview. Hold on one second. Okay, so viscoelastic characterization, we looked at very quickly there with that ointment, but viscoelastic characterization can also tell you quite well how the material is going to behave at rest. So as we go to lower frequencies, and you see the material at lower frequencies, this indicates how it's going to be at rest. If the phase angle goes up towards 90 degrees, that indicates that it's going to be a liquid. And you can see here the viscous modulus in blue and the elastic one in red. Now, if the viscous modulus is higher than the elastic modulus, this indicates that the material is actually going to flow like a liquid. And so we see here with silly putty that the viscosity is coming up and then it reaches a plateau. So it's actually a liquid over a long period of time. I don't know if you've ever played with silly putty, but you can roll it up and bounce it on the table at high shears. But you can also leave it on the table and it will flow out into a puddle over a period of time. On the contrary, if you look at hand cream, this is actually a viscoelastic solid. And you see as you go to low frequencies, the material is elastically dominated all the time. And the viscosity seems to just go up and up and up and up as you go to lower and lower frequencies. So this indicates that you have a yield stress, whereas this is a zero shear viscosity. So the frequency sweep behavior from a viscoelastic frequency sweep in oscillation can give you an idea of how the material is at rest and whether it's going to be stable. Now, this is another area of research is artificial synovial fluids. And one thing that the FDA have done is approved hyaluronic acid for use in synovial fluids. And so people actually can have hyaluronic acid imparted into their joints here to give more cushioning. So when you're a young person, this would be the frequency sweep trace for your synovial fluid here. You see it's viscous at low frequencies in this case and can flow around, but at high frequencies, when you walk or when you run, you can see it's actually elastic. And so this gives you some cushioning. So it can flow around, but when those joints hit together when you're walking, it's going to give you a kind of a gel structure between the joints, and it's going to give you some cushioning. And if you're running, it's even more elastic, so your joints don't hurt at all, and that synovial fluid is really doing a good job. Now, when you get older, the elasticity drops, and you can see here the red line and the viscosity drops too, but you can see then that walking actually might cause some pain because you don't have very much cushioning in that joint. It's actually a liquid, and so it flows out in the time scale allowed. Maybe the cartilage is hitting on the cartilage there, and it's a little bit softer, a little bit more painful. Running, however, might be okay. When I gave this presentation once in California, the guy said to me, "I completely understand now. I can walk. I mean, I can play tennis fine, but I can't walk for very far before my knees hurt." Somebody with osteoarthritis really has lost nearly all of their elasticity in their synovial fluid. And so running or walking is giving you very, very little cushioning at all. And it's just a watery liquid between your joints there. So if we add some hyaluronic acid, which is of a higher molecular weight, then actually this will put back in the elasticity that we want. And so this is our running timescale, this is our walking timescale, and you can see here this is going to be elastically dominated at both of those frequencies. And so they say for checking if the material is going to be high enough molecular weight, you need to have a crossover frequency of your elastic and Burgess modulus below 1 hertz. That would make it high enough molecular weight. And in this case, we've got 0.1 hertz. So this is actually very, very much stiff enough. And we have ophthalmic fluids. They need to have a crossover frequency of less than 0.5 hertz. I'll speak about that in a minute. So the other test is for viscosity at low shear rates. So the hyaluronic acid flow curve needs to have a high enough 0 shear viscosity. So it is a liquid at very low shear rates. And the viscosity here indicates the molecular weight. And rather than take these samples for GPC and spend a long time doing this, you can measure it quickly with the viscosity flow curve and see at low shear rates, we have a high viscosity. So it is over 200,000 millipascal seconds at 0.01. Or for joint supplements, it needs to be over 20,000. That's the second line here at 0.01 reciprocal seconds. So the reference to ophthalmic implants is actually that if you've had a cataract operation or some other operation on one's eye, you can replace the viscous humor with hyaluronic acid. Obviously, it needs to be very jelly-like, very thick, to stop any leakage afterwards. And so this has to be a very high viscosity and also has to have a lower crossover. Now, another use of rheology is the formulation of eye drops. And often eye drops have a pharmaceutical ingredient in them, but it's often lost. And so we don't have very good bioavailability. They say that maybe only 1 to 10% of that drug actually stays in the eye because of the amount of tear drainage. And so you'd be losing between 90 and 99% by blinking and tear drainage. So if we can increase the viscosity here of this eye drop, it will actually stay in the eye for a longer time. And so this is water, maybe about 0.8, 0.89 centipoise, millipascal seconds. I guess we're looking at 30 degrees C. But an eye drop here is about 5 times the viscosity of that. So we've thickened it up, and now it can actually stay in the eye, and it will give you slightly better lubrication, and it will also keep the drug in the eye for a longer time. Another way that people have done this is also by adding a hydrogel, and this is a hydrogel that gels up on heating, and so you can see here, obviously the eye is at a warm temperature, maybe about 35 degrees C, and at room temperature or fridge temperature, the eye drop is a liquid, but then as it warms up, it becomes a gel here. And so we have a time for it to gel up, depending on the temperature. So the idea is that you drip the drop onto the cornea, it has a chance to level out, and then it will gel up. So there's a leveling time, which is critical here. If it gels up immediately, then you'd obviously have small gel particles, which wouldn't be very comfortable or effective. So we need a chance to level out, to make a thin coating across the eye, and then to gel up after a certain time. And that will then give you a clear film, which you can look through. So it's giving you a protective coating, it's holding the active pharmaceutical ingredient in contact with your cornea, and giving it a therapeutic healing effect. So this is a very good simulation. If you're doing an oscillation test with time, you can see it's a viscously dominated material and then thickening up to an elastically dominated material over time. Now in the R-Space software that comes with the connectors, it actually guides you right through all of these steps. So you can have in the sequence, enter the temperature, enter the amplitude sweep properties if you like, enter the frequency sweep properties, and then go to the temperature that you want, run an amplitude sweep, do an analysis, find the linear region, and then go straight into a frequency sweep and see the crossover frequency and things like this. So the built-in tests in the Connexus software make this much more easy than maybe one might imagine. And also it gives you good reproducibility across different users. Obviously, these standard operating procedure tests take away the randomness of time delays and loading and the way that the sample is loaded and trimmed like this. It gives you exact volumes for loading a sample. So you can pipette the sample on, or you could just use a syringe here, but you could actually load exactly the right volume if you pipetted it on here. And this is some screenshots from my sequence when I ran those topical creams earlier, the eye ointment samples earlier. So you can have a splash screen here with your logo on it, and then click next. And it says, do you want to load a new sample? It seems that you have one loaded already. So if you say yes, it will open the gap and then allow you to have a new sample loaded, ask you for the sample name. So obviously you can type in the batch number and any information about the sample, formulation details, things like that. And here's a picture of me loading an ointment onto the lower plate. It's going to tell me the exact volume needed, and the plate diameter is all calculated, and the gap used is going to be calculated in that. And then it's going to prompt you to trim it, so you only have the right volume of sample there, and then close the hood, so you know when to close the hood. And then after the test, obviously the test will proceed, and we'd have lots of data tabs here that you can go through. But after the test, it tells you, do you want to unload the sample? You just hit yes or no. And then it tells you to wipe it off as it's unloaded, and then save the data. So you can save the data wherever you like. And it really very much more simple. So if you want to get the same result across all the different users in your lab, then the Connexus with the RSpace software is a good option. So in summary, Rheology is a very useful tool in the pharmaceutical industry, has multiple applications and uses. I've only touched on some of those, but you can see there are many of them. With the RSpace software in the Connexus and the standard operating procedure sequencing, it really helps you to generate robust and reproducible data. The data is useful for lots of areas of formulation, processing, and end-use simulations, and also we can use it to show equivalence for an FDA ANDA application if needed. So thank you, and I will now pass back to Malena. Any questions?
Well, thank you, Phil, for this nice presentation. I have some questions are already here, and there's one that I can even answer. It's from Mina, and she asks if the seminar will be available on the web later, and I can say yes. You will receive an email with the recording, and it will also be available on the NETCH website under Literature and Digital Media. So, Phil, are you ready for some questions?
Certainly.
So the first question is, which parameters should I take into consideration when I want to decide how long I wait for the sample to regenerate the inner structure after loading before measuring?
That's a good question. And I think when you're considering any parameters for any rheological test, it's good to consider what you're characterizing and why, and then maybe to try to simulate that event. For instance, if you waited for the sample to be fully structured on the rheometer and maybe take over 5 minutes per sample for rebuilding, it obviously will become maybe half an hour even for some samples and things like that. Could become less convenient to run a bunch of samples. But if you're simulating an eye drop rebuilding, maybe you don't need to wait that long, right? So, or if you're looking at something as it comes out of a mixer or out of a pumping device, you wouldn't want to measure it fully structured anyway. But if you're looking at the storage stability, then obviously, yes, you would want to load the sample and wait for it to be fully rebuilt before doing that test. And so it may take you 5 minutes for the sample. Now, one test I would do then is the amplitude sweep, first in oscillation to see the linear region. And then I would do a pre-shear and then an oscillation in the linear region to watch how long it takes to rebuild. And if the sample is fully rebuilt after 1 minute or 30 seconds, then obviously after loading, I can wait 1 minute or just 30 seconds. But if I see that it's still rebuilding considerably after 5 minutes, then maybe I need to decide on a time that's convenient to work with. So sometimes it's just really inconvenient to wait for the sample to fully rebuild, like a yogurt. Turning back into a gel after you've stirred it might take hours, you know. So rather than wait hours, you could just say, you know, I'll share the samples and then I'll always wait 5 minutes. And at least then, although they're not fully structured, I'll get a reproducible result because they will all have had the same shear plus a 5-minute rebuild time. So yeah, it's a complicated question. Sorry to give you a long answer.
Thanks. I have a question here. In the case of a gel, which parameters should I take into account for evaluating if the gel behaves as a chemical gel or as a physical gel?
That's a good question. So a chemical gel usually would be a liquid that after a set time has cured or undergone some reaction to form a gel. I guess that's what is meant by that. And often if you break a chemical gel, it doesn't reform. You actually undergo what's called rheomalaxis. It's a permanent breakdown of the structure. For instance, if you tear a piece of rubber in half, it's not going to turn back into a whole piece of rubber again unless you melt it, right? So if it's a viscoelastic material, sometimes they do heal over a period of time. And so you could do shear and oscillation to watch the rebuild after breaking the sample. So shearing it obviously would destroy it, and then oscillation could be allowed to rebuild it and see the structure rebuilding with time. I don't know if I answered the question. Is that right, Milena?
I guess. You are the expert.
Any more?
Let's see. I have a question. Wait, now I lost it. Where is it? So someone asks if you know if there are any studies that couple the fluid rheology, fluid surface tension, and applied surface wettability. So do you know any?
Are there any studies that do that? Often for paints, spray paints particularly. Yep, the surface tension comes into it because obviously you want a lower surface tension for it to continue to wet the surface. If you spray plastic, for instance, often the surface energy isn't high enough to stay wetted out, and the paint will recede after being sprayed on. So for instance, if you splash water on a plastic coating, it will recede back, right? It doesn't often just stay as a thin layer of water. But if you reduce the surface tension by putting a little bit of washing up liquid in there or something like that, then you can keep that surface completely wetted. So the other way of doing it is increase the surface energy of the substrate that you're coating, maybe by flaming the plastic or something like this. And so the wettability of the surface is very important. Surface tension plays into that, as well as viscosity for atomization and sprays. So actually there are multiple studies where these things have come in, as well as maybe inkjet printing. I think there's multiple studies on inkjet printing because you can print different substrates, and the rebuild time also comes into that. So yeah, there's a lot of different aspects of the physicochemical properties which play in together with these things. Now for pharmaceuticals specifically, I think you probably could spray topical creams, you could spray nasal sprays, although I don't know if you'd have a wettability issue with that. I'd have to think about it. Maybe the coating of tablets may bring in some of those factors. Yeah, I'd have to think about it. If you'd like, please do email me, and I'll be happy to try to answer that in more detail.
Perfect. Are you good for one more?
Certainly.
So this is a good one. What is the advantage of using rheometers in comparison with viscosimeters?
Oh, yes. Okay. So a rheometer obviously has temperature control, and so you can dynamically simulate a real use environment. For instance, the heating of when the eye drop hits the cornea, you can do that on the rheometer because you can heat the plate up very quickly, actually. Or when you spray a nasal spray into somebody's nasal cavity, or if you're doing in vivo, in vitro studies, then the very fast temperature control, plus also a lot of these tests are viscoelastic characterizations. You're looking at the rebuilding time, or the gelation time, or the structure rebuild after shear. Now, viscometer can only do different amounts of shear rate, right? You can go from low shear rates to high shear rates, but even then you can't get to very low shear rates. So on a viscometer, you're going to be limited to, as I say, the mixing, pumping, and maybe low shear spraying behavior. So you can characterize spraying, but you can't characterize rebuild time, or sagging, or sedimentation, or leveling, or runoff, or gelation time, or gelation strength. So there's a whole lot of aspects of a rheometer that you can measure all these properties. Also, you can do squeeze flow and pull off, attack testing, and things like that. So transdermal patches, delayed release vehicles, the viscoelastic properties will be related to the release time for that API through the medium. So Rheology can really help a formulator for pharmaceuticals, I think, a lot more than maybe a viscometer. And I would say that it's possibly underused right now. It's a fairly new market, and people are a little bit afraid of getting into rheology, but it's certainly become a lot more simple with the advent of these newer rheometer systems and the user-friendly software.
Perfect, thank you. So I think this brings us to the end of our Q&A session. So forgotten, and we will answer them via email. Yeah, thank you very much for attending and for all of your questions. I had a question again about the recording. It will be sent to you in an email and is also available on the NETCH website. And please look out for the webinars that are coming in the next month. And thanks again, Phil, for your nice presentation.
Thank you, Milena. Thank you, everybody, for attending.
See you next time. Bye.
Thank you. Bye-bye.